What do you know about stars? Probably that they're the bomb, figuratively and almost literally. Well, most people know what they see every day and learn about in school or through articles. The sun is a star. It's really far away, and it's pretty bright, and it rises and sets from our sky as we revolve around it. But what do we really know? Well, I'm here to tell you and show you the ins and outs of why some of the hottest celestial bodies in our universe are so cool. The sun is one of various stars that exist in our galaxy. A star is a luminous sphere of plasma held together by its own gravity, our sun being the closest to Earth. The next closest star to us is Proxima Centauri, 4.22 light years away, so pretty far. Stars are born here, in clouds of matter known as nebula. These celestial birthing pools are home to various amounts of matter. The process of sun forming starts when a particular chunk of matter begins to combine with other amounts of gas and dust. As this chunk takes on more matter, it begins to compress. It is pressed together tighter and tighter until eventually it begins to heat up. It's now known as a globule. Eventually this globule begins cooling as it compresses even more, all the while spinning faster and faster, creating a lot more centrifugal force and more friction. This causes the sphere to heat up again. And bada bing bada boom, you got yourself a happy new little protostar. Very nice. It's at this point the amount of heat begins to get serious, as the star continues to heat up to 27 million degrees. Pretty hot stuff. Once the protostar reaches this temperature, it begins the process of nuclear fusion. Nuclear fusion is a nuclear reaction in which two or more atomic nuclei collide at a very high speed and join to form a new type of atomic nucleus. In this case, hydrogen atoms smash together and start forming helium. The process of nuclear fusion, as well as creating helium, releases a lot of energy, mainly in the form of light and heat. The fusion retains the star from shrinking any more than it has and maintains it for the lifespan of the star. Congratulations! A new star has just been introduced in the universe. After about 100,000 years of development, but that's nothing but a couple of minutes in terms of science time. This process applies for all stars, although not every star is the same. Our humble little sun is what is known as a yellow dwarf. Yellow dwarfs, like our sun, have about 0.8 to 1.2 solar masses, one solar mass being equal to one sun, and a surface temperature of between 5,300 and 6,000 Kelvin. There are various different types of dwarf stars, yellow dwarfs being fairly in the middle, all of which are called main sequence stars, as this is the stage in which a star is what amounts to its adulthood. Starting at the coolest of the cool is the brown dwarf. Brown dwarfs are the tragic failed attempts of stardom. These types of stars never gain enough mass and heat to begin nuclear fusion. As a result, they have a very low temp and luminosity. So tragic. Next is the red dwarf. Red dwarfs are low mass and low temperature stars. Red dwarfs range in mass from as low as 0.075 solar masses to about 0.5 and have a surface temperature of less than 4,000 Kelvin. Red dwarfs are the most common types of star, at least in the Milky Way. But due to their low luminosity, you can't see many of them without high-tech gear. Orange dwarfs are next. Orange dwarfs are intermediate in size between red dwarfs and yellow dwarf stars. They have masses of from 0.6 to 0.9 times that of the mass of the Sun, and surface temperatures between 3,900 and 5,200. But let's not forget, not every star in our little universe is a dwarf star. These stars are actually quite big. Very big. Like, super big. Some are so big, even Jupiter's like, dang. These giants are somewhat similar to dwarf stars in their color, but way freaking bigger. From 8 times out of our Sun to 100 times out of our Sun. A star becomes a giant star after all the hydrogen available for fusion at its core has become depleted, and as a result, it begins to expand. Giant stars, or even the bigger supergiant stars, come in the red, yellow, and blue variety, similar to that of their dwarven brethren. But one of the big differences, get it? Big? Is that giant stars tend to be much older. In fact, stars expand to the size of giants when they get closer to dying. Yeah, stars don't live forever, but stars don't just blow out like a light bulb. As the star continues to gobble up all the hydrogen and turn it into helium, it begins to run out of power. Eventually its supply is depleted, and it begins to expand as it eats up any energy still left. Once there is not enough to sustain itself anymore, it begins to disperse, and the star is no more. Well, almost. As the outer layer dissipates and is flung into space, a single small star, also called a star remnant, is left. This remnant is known as a white dwarf. White dwarfs are very dense. A white dwarf's mass is comparable to that of the Sun, and its volume is comparable to that of the Earth. Its faint luminosity comes from the emission of stored thermal energy. Considerably massive stars go through a different process. As they get old and their fuel source is used up, it begins to compress again. Eventually it compresses to such a degree, the amount of energy bottled up is released and the star explodes in a wondrous detonation of matter known as a supernova. It's at this point a star turns into what is known as a neutron star. Neutron stars are a stellar remnant of a giant star left over after a supernova. Stars 1.35 to 2.1 times more massive than our Sun form neutron stars when they die. Neutron stars are the densest and smallest stars known to exist in the universe. Stars that condense massive enough can also form into another entity upon death, known as a black hole. Black holes occur when the star condenses so tight its gravitational pull becomes inescapable. And from our research, that is really literal. Literally nothing is able to escape its gravitational pull once it comes into effect. Black holes literally bend time and space before us as it pulls in even light. That's right, even light. The fastest force in our knowledge can't escape, and is pulled in by the black hole. It is even believed a black hole is present at the center of our galaxy, and that it is because of that all the stars and other bodies in our galaxy orbit like it does. So, yeah, pretty crazy stuff. So when we look back, stars have some pretty crazy lives, starting from a celestial breeding pool and forming into nuclear fusion creating energy balls over the course of 100,000 years, living for 100 billion years if they are around the size of our Sun, or 100 million years for bigger stars due to an increased rate of fusion due to size, coming to a point where the fuel source runs out and then expand to monstrous sizes, and finally bursting or receding to a small white dwarf, or for bigger stars, exploding into a supernova and ending up as a neutron star, or if massive enough, turning into a light-absorbing black hole. Most stars you see in the night sky are actually two star systems, or binary star systems. They are so far away, however, that they just appear as one speck of light. Consider that the closest star to Earth is approximately 4.2 light years away. It would take about 70,000 years in our fastest spacecraft to reach it. There are approximately 400 billion stars in the Milky Way galaxy alone. On a clear night, you cannot see even a fraction of these stars. However, during a clear night in the country, with the naked eye, you can see up to that number miles away, very easily. The original materials that make up all stars within the galaxy were formed during the Big Bang. The most common type of stars within the universe are red dwarfs. These stars are common due to their low masses and the fact that they live for a very long time before turning into white dwarfs. The coolest stars, excluding the brown and black variant in the universe, are red, and they sit at around 3,500 Kelvin. Opposite to that, the hottest stars, excluding neutron stars, are blue due to their incredible mass and the amount of chemical reactions occurring within them. They burn at around 6,000 Kelvin. Some neutron stars rotate very rapidly. up to 716 times a second, or approximately 43,000 revolutions per minute. Black holes don't suck. They actually just have such a high amount of force of gravity. It's more like being pushed into the black hole by its gravitational forces. There are types of stars that don't even exist yet, but scientists believe and theorize may actually come to be. Black dwarfs being one of them. Not believed to exist yet, as it would be older than the universe due to scientific calculations, but is a theory of what happens when a white dwarf loses enough heat and light it doesn't glow anymore. So, yeah, pretty cool. That's all I have for today. Thanks for looking, thanks for listening, and thanks for learning. This is Shayne, signing off. No, seriously. This is the end. You can go home now. Okay, bye.